of a graphical form. So if there were symbolic forms, there had to be graphical forms too. And graphical forms, again, are a way of looking at a graph and through student interviews recognizing, well, how do students use certain kinds of features on a graph? And that's turned out to be really helpful, not only in just the enzymes work, which is actually all the blue squares that you see, but in some work that we did with Maya Elmgren and Felix Ho, and I know Felix is in on this call, and some work that Johnny led up actually in enzyme kinetics with two other undergraduates, with Sven Phillips and Nick Hux. So that kind of gives you a sense of this big, huge research program where we used a lot of different kinds of frameworks. But I'm going to spend some time talking a little bit about covariational reasoning, because it is something that we use all the time. It's like the air we breathe in chemistry. We just use it constantly. And from the mathematics education literature, what you can get figured out is that students have a really tough time with it. Okay, so what's covariational reasoning? So it just means you're going to coordinate a relationship, excuse me one sec, between values. So Saldana and Thompson in 1998 defined it as holding in your mind the sustained image of two quantities simultaneously. And what Kinsey and Johnny wrote about in 2019 is that you're attending to the relationship between the values with an emphasis on how do they change, okay? And this is really fundamental to math and science. It helps you reason about graphs, it helps you reason about equations and functions, and it helps you conceptualize problems. And now here we're gonna do something rather crazy. So Heather Johnson is actually a mathematics education researcher, and she is tremendous. She's a tremendous follow on Twitter. And I'm going to lead you through one of Heather's activities that supports covariational reasoning. So hopefully this is going to work. We're going to get there. Okay, it's coming. It was there just for a sec. Oh, it's coming. We're going to do something called the toy car. Okay, so you do need, if you don't have it in front of you, if you have a pencil and a piece of paper, if you don't have a pencil and a piece of paper and you don't feel like going that high tech, you can use your finger because you're going to graph and draw some things. So first thing I want you to do is just watch this little car and see how it moves. There we go, coming around. Okay, so there you go. Now, next thing we're going to do, we're going to go through this activity. So we're going to investigate the toy car's distance from the shrub and the total distance that it traveled. So what you're going to want to attend to are two things. How far is the car from the shrub? That's the dotted line. And how far has the car traveled? Okay, so those are the two things you're going to watch and look for. Okay. Now, here's what we're going to do. So here we have our car, back to the start point. Here we have our shrub. And over here we have something that looks like, okay, we're going to get to graph. That looks exciting. So the distance from the shrub is on the y-axis. The total distance traveled is on the x, okay? And all we want to do is move the dynamic segment to show how the toy car's total distance traveled is changing, okay? So what I'm going to do is I'm going to watch the car and I'm going to move this little purple blob to show how the total distance traveled changes, okay? So here we go. I'm going to start the car and I think, okay, well, it's traveling along. It's traveling a little farther, and a little farther. And hopefully you're going, yeah, if I had control of the screen, that's exactly what I would do. I would have scooched that purple blob from the left over towards the right, okay? Now, what we're gonna do, ooh, this one's a little tougher. We gotta think about, as this car moves, how does the distance from the shrub change? So I'm not going to move it on the first try. I'm just going to run it and let you think about it. Okie doke. So then I'm going to rerun it here. Okay, here goes the car. So it gets a little bit farther away and then it turns and it gets closer and closer and closer and then it starts to move farther away again. So what I've done here is the two things that I'm attending to, I've looked at them one at a time and thought about, okay, how do they change? Okay, now what we're going to do is in this part of the simulation, what's going to happen is the dynamic segments, so these purple segments, they're going to show how the distance from the shrub and the total distance change together. So I don't have to move anything. I'm just going to start the car moving. Okay, so the neat thing about this simulation is it lets you see how do these two things change together, but they're just crawling along the x-axis and the y-axis. And so then, of course, the next thing to do is to ask you, okay, in a single graph, represent how the toy car's distance from the shrub and the total distance traveled change together. So this is the heart of covariation. You've looked at one variable, you've looked at another variable, you've attended to how are they changing, and now you're going to try and figure out, okay, how do they change together? So I'm going to say, okay, it comes up, and then it goes down, and then it kind of comes back up, okay? So I can tell you in the way that Heather uses these things in her classroom, she's really purposeful about having students attend to one thing at a time and then attend to something together. And then the students are able to make their own drawing, and you can even change the colors. I don't know if you can see the little color ball right here. So I could, I could change what color I wanted to put on there if I wanted to. And what she is able to see is she's able to see a whole classroom's worth of graphs from different students. So then you can show students the graph, and although it has that nice curvature to it, there are students who will draw a graph that actually is a straight line. And so you can tell that they're having trouble in terms of thinking about how do these two things vary. And I can share these slides afterwards. There's a whole nother simulation that she walks you through. Oh, sorry, let me go back one. Boop, boop, boop. Where you do total distance traveled now on the y-axis, and then, oh wait, nope, hold on. And distance from the shrub, yeah. So you get to do a whole nother one. So let me get back to my PowerPoint. Okay. So hopefully, so I know not everybody loves math and chemistry together. So I hope by walking through that little activity, it gives you a sense of what covariational reasoning is all about. And one of the things that's sometimes pretty tough is that we know a lot of chemistry, and it's hard to remember back to a time where we didn't know a lot of chemistry and the problems that students would have. And so actually having you move through that activity with a toy car and a bush and looking at the distances and how do you represent that helps you sort of get out of your chemistry mode and get into a mode where it's like, okay, let me see what this, let me try and figure out what's going on here. So it's a more student-like experience. So in terms of covariational reasoning, Marilyn Carlson is usually the person that you see get cited. And you often can see this framework that she has developed. And the idea is that, for example, if a student can engage at level number 3, they can coordinate the amount of change in one variable with changes in the other. They can do level 2 and they can do level 1. But what they can't do is think about an average rate and an instantaneous rate. And those concepts, Marilyn is a mathematics education researcher. So those concepts of average rate and instantaneous rate are really important in mathematics. So those are the kinds of things that they would think and deem are important, and they want to know where a student lands on these covariational reasoning levels. And I would say to harken back to the resources framework, that, you know, a different context, a different prompt, a different problem can indeed have students landing at a different level. So one might envision that if a student who's a chemistry major has done a lot of kinetics, they might say, yeah, I know what an instantaneous rate is, and I can talk about how variables change with one another. I can talk about average rates, instantaneous rates. But if you give them a problem in a physics context, an engineering context, an economics context, they may have a heck of a time you know, with that kind of covariation. So just keep the resources framework in mind as well. So one of the really tough things that comes up then when you talk about covariational reasoning, and it is true for all the sciences, is that this covariation is inherently chunky, okay? And it, very often what we do in lab is we go in and we take data, okay? And we don't take necessarily 10,000 or 20,000 data points. You know, if you think of a general chemistry lab, you know, students are taking, you know, 5 or 6 data points in some cases. And they're, you know, if they're building a standard curve, they've got 4 or 5 and that's it. So to us, this covariation is really chunky, but here's one of the things I want you to know. So first of all, and we're going to get to a slide in just a sec. Sorry, I'll pop forward one slide where these references are that are really important, but they're also on the bottom of this slide. So chunky versus smooth covariation. One of the things you need to know outside of your discipline of chemistry is that mathematics very, very, very much privileges smooth covariation over chunky. They want students to see functions as emerging smoothly and continuously. So if you are one of the people who, when you saw that little car and bush demo, and we attended to one variable, attended to the other, and then we attended to them both at the same time, in your mind, the function just exploded out of it and you could see the curvature. That's what mathematicians want. What's difficult is that's really problematic in the sciences. So I will just do chemistry, physics, and biology. Our data is by necessity chunky. And all of our experiments have a context, and the things that we measure are real attributes of real objects, and many, many cases they have units. And in mathematics, that is not how mathematics gets taught. And so no wonder, you know, some of the time there's a difficulty between what a student learns in a math class and what they learn in a chemistry class. Another way I've heard it discussed and framed is that between the sciences and mathematics, we have the same vocabulary, we just use different grammar, is another way to put it. Another one that I'll put up here just to call it to your attention is there's 2 papers about derivatives that I've got on the bottom here. The first one is the Dre paper. So it's Tebby and Dre, Corinne Montague, and David Roundy are the big 3 on that paper. And they wrote a paper about interpreting derivatives. And then Stephen Jones wrote a chapter for us in an ACS symposium book called It's Just Math, Research on Student Understanding of Chemistry and Mathematics. But what Stephen really tried to do was help chemists understand from calculus research you know, what does that imply for chemistry instruction? So the Tevye and Gray group, one of the things that they have done that's really important is they probably had for 10 years discussions between physicists and mathematicians. And so they've, through their discussions and many papers at the room meeting, they finally published this Primus paper about interpreting derivatives. And, you know, one of the things that they did that was really important is at the end, they came up with some ideas about teaching calculus that might be helpful to students who are then taking science classes. So the emphasis on examples, not counterexamples. So don't show all the counterexamples to students. Help them build out their knowledge and recognize what resources can be used productively by doing, you know, real examples that are helpful. Use numerical data and discuss and determine derivatives experimentally. I mean, goodness, we actually use derivatives, right? In second semester general chemistry. Use infinitesimals. I won't touch because there may be people who are saying, what's an infinitesimal? This is like, I'm having horrible thoughts of my calculus class in college. But emphasizing conceptual understanding and that numbers have meaning and graphs have meaning, that's something all of us can get behind. So again, I'll put out these slides, but those are the 3 references that you want. If somebody's grabbing their phone and taking a picture, should be able to get them through your library and such. And then, you know, one of the things I want to urge people to do is, you know, going across the disciplines is really, really interesting. And I think Ginger asked a question, I think on Twitter this morning, about, you know, getting to know people on your campus inside and outside of your department. But also, so on your own campus, you can have people who are outside of chemistry who are interested in mathematics education research, biology education research, physics education research. But you can also, you know, get to know people on other campuses and in broader communities. And what I would say is be brave, ask questions, and introduce yourself. You might find you develop some new collaborations and make some great friends, and sort of learning what is it about your discipline that makes it your discipline. How do you think about certain things? How do people outside of your discipline think about certain elements and things? And then it helps you understand a little bit, well, why might students have difficulty with this? And Melanie Cooper and Mike Klimkowski have done a lot of that across biology and chemistry, for example. But it's just a really great thing to do. And the thing I would tell you is that being in different intellectual sandboxes, it's just a joy, because you can learn different methodologies. All of the papers that you saw where you were like crying out loud, that's not a chemistry journal. You know, I learned about those papers and those researchers from reading research in mathematics education, and actually from going to a conference called ROOM, Research on Undergraduate Mathematics Education. My folks in chemistry, it's one of the few chemistry you know, groups that's there. And then there are some physicists too, but it's just a joy to be in a different sandbox. So, last but not least, I know we have talked a ton about methods this morning and had some just tremendous talks and lots of different ways to think about designing studies. But one of the most important things I would tell you is that the best methods in the world won't mean much if you ask trivial questions. So as one of the old lions in the field, or lionesses, whatever it is, I would say be brave and ask interesting stuff, okay? It's really important to ask good questions and then have solid methods. But if you ask crappy questions and they don't lead you anywhere, then you're kind of like, oh, dang it, I wish I would have asked something better. And then one of the things lots of people know about me is I really, really like Disney. So this is actually a set of Pixar videos that run on Disney Plus. Forky really did ask all those questions. So some acknowledgements. So Kenzie, Alina, and Johnny were the graduate students that I had that worked on the big kinetics project. Tom Holm was the evaluator. We had generous support from the NSF. And in addition to all the papers that we published, we got an ACS symposium book out of it with chapters by many of the researchers who are actually in on this Zoom-posium. As well as 2 chapters that came from the mathematics education world. So Stephen Jones's chapter is in there, and Annie, oh heavens, I can't remember Annie's last name. Annie is in there with the group theory chapter. And last but not least, I think the community wants to give a big round of applause and a thank you that, you know, when COVID-19 hit and it just became so apparent that we were not going to be able to travel, and to do things as we had done them, that Ash and Michael got it together and managed to blow out the size of MISR, and we're going to run it 3 times. And one of the amazing things that, you know, Stacy, Larry, Brett sent me a text this morning, you know, when you look down at the bottom and there are 240 participants, that's bigger than a GRC, you know, so there are lots of people really hungry for this information. So thank you so much to Michael and to Aisling for putting this together. The community really appreciates it, and we're very thankful and very grateful. I'm going to escape out of this. Stop sharing.
All right.